Hi, my name is Jaden Gethers, and today I'll be presenting our work on stochastic grade, a system for grading and clustering student programs that produce probabilistic output. For a bit more context as to what this title means, we will refer to programs that produce probabilistic output as stochastic programs, and thus our automated grading framework for evaluating stochastic programs is aptly named stochastic grade. Stochastic grade offers four main benefits. First, it offers an up to 1,000 times grading speedup relative to a reasonable baseline. It offers theoretical grading error rates, or the rate at which it makes an incorrect grading prediction. It offers clustering by error type, facilitating tasks such as partial grading. And lastly, it handles multi-dimensional outputs. But why do we care about grading stochastic programs in the first place? Well, there are three main points of motivation. First, stochastic programs are fundamental in several areas of computer science education, from machine learning and cryptography to introductory computer science courses. And here we have an example of a creative application of stochastic programs in which students generate art by sampling circle radii from a probability distribution, giving an aesthetic representation of this programming paradigm. Moreover, automated grading facilitates efficient and objective evaluation, removing the burden of grading from academic staff. And lastly, but certainly not least, automated grading of stochastic programs is underexplored. And to the best of our knowledge, there are no known published solutions in the EDM community for automatically grading stochastic programs. This is a hard problem. But what makes grading stochastic programs so hard? Well, first, outputs are variables, so we can't use methods that rely on determinism. We need a method that embraces randomness. And fixing the seed of the pseudo-random number generator doesn't always work. Here we have an example of two programs which are semantically equivalent, but produce two different results when fixed under the same seed. So we need a grading method that can embrace randomness. Our first attempt is to grade using hypothesis testing, wherein we collect samples from the student and solution programs and compare their similarity using a disparity function to measure the difference between them. Then, using this disparity metric, we can test the null hypothesis about if the program is correct. And we do this by comparing our disparity metric to a rejection threshold. If our disparity metric is less than the rejection threshold, we accept the null hypothesis and state that the program is correct. Otherwise, we reject the null hypothesis, claiming that the program is likely incorrect. And here's a visual representation of standard hypothesis testing in action. We perform a single hypothesis test at a fixed sample size with a fixed significance level. And after performing this test, we can determine whether the program is correct or incorrect. Now, there are several pros and cons to this method. One benefit is that we can control the false rejection rate, which is the rate at which we accidentally mark correct programs as incorrect. So it's the rate at which we make a wrong prediction for correct programs. And this false rejection rate is precisely given by alpha, the significance level. So alpha is the fraction of correct programs that could be the maximum fraction of correct programs that could be marked as incorrect. It is also configurable in that we can select the number of samples we'd like to use and collect, or the disparity function we want to use to compare them. However, one of the biggest problems with this method is that we don't know how many samples we need to generate. I mean, do we really need 400,000 samples to detect differences as discrepant as this? Collecting the same number of samples, and a large one at that, leads to inefficient runtime, especially when we don't really need that many samples in the first place. So this motivates our approach, stochastic grade. Rather than performing a single hypothesis test, we perform a series of hypothesis tests at different sample sizes with controlled significance levels. These controlled significance levels allow us to still guarantee the same false rejection rate. But we see that instead of only sampling at one fixed sample size, we sample at a series of different sample sizes, so that programs that are largely discrepant only need around 400 or fewer samples rather than the full 400,000 samples to be detected. We see that we're increasing the significance level at each step by factors of 2 to guarantee our same false rejection rate, and more samples gives us more power with the test in order to detect finer differences between programs. So the largely discrepant programs are detected early on, but programs that are closer to the solution may need more samples. Now, this diagram in itself can appear a bit confusing, so let's focus on a single block. We realize that each gold block in stochastic grade is just a single hypothesis test, and we're testing the same thing as in standard hypothesis testing. We are looking at whether the program is correct or not, using the disparity function and comparing the result of the disparity function to the rejection threshold. Again, if the disparity metric is larger than the rejection threshold, we mark the program as incorrect. Otherwise, we keep sampling, trying to increase the power of the test until we reach a maximum sample size, at which point we can mark the program as correct. For more details about what the significance level is and how we can still guarantee the false rejection rate, you can look at more details in our paper. And for the disparity functions, we tested a variety of different disparity functions. We won't go into too much detail about each of these, but different disparity functions can be used within different problem settings. There are several benefits and features of stochastic grade. One of them is that it offers exponential speedup on grading incorrect programs relative to the standard hypothesis testing baseline. However, like standard hypothesis testing, it retains the error control on the false rejection rate, which is again the rate at which we incorrectly mark correct programs. And it retains the configurability with the sample sizes we use as well as the disparity function. It also supports multi-dimensional output with a method known as random projections, which you can find more details about in our paper. To evaluate the performance of stochastic grade, we tested it on data from Stanford's CS109, which is a probability for computer scientists course. We tested it on 4 different assignments to see how well stochastic grade performed in different problem settings. In the first assignments, we test how well it can detect subtle translations, and then how well it can detect differences in the extreme regions of probability distributions, how well it can detect differences in programs that produce multidimensional output, and lastly, how well it works with programs that require input arguments in order to produce output. And we have 4 main experiments we're testing. We're looking at the accuracy of correct programs in order to verify the theoretical false rejection rate or error guarantee that we claim. We sought to test the accuracy of stochastic grade on incorrect programs to see how well it adapts to a variety of different student errors. We test the runtime relative to the baseline standard hypothesis testing method to show the exponential speedup. And lastly, we evaluate its performance on clustering. With the accuracy on correct programs, we see that even with scores that may need to use estimates and can't exactly adhere to the theoretical guarantee, all of the accuracies align with the expected false rejection rate given by alpha. So we see that each of the items in the column corresponds to the false rejection rate given in the row header by alpha. Then for the accuracy on the incorrect programs, we see that stochastic grade achieves at least 98% accuracy with 1 score in each problem. And the scores are different from problem to problem, which highlights the benefits of being able to configure the scoring metric or the disparity metric to your problem. We then saw how well stochastic grade did at saving runtime, and in many cases, we observed the exponential speedup relative to standard hypothesis testing, seeing a large sample size saving of up to 1,024 times relative to our standard baseline in all of the problems. Lastly, we talk about clustering, which is useful for providing information beyond mere binary signals of correct or incorrect. In fact, clustering by the error types allows for a richer evaluation through partial grading and even an error analysis of the different student programs. And disparity measures that we get from our disparity functions yield a simple and effective clustering. We can compose these disparity metrics in order to yield an even richer feature representation of the program. So by using each of the disparity metrics we calculate, we can put them into a single vector for a better representation of the program, which improves clustering performance. Indeed, multiple representations does improve clustering performance, whether we're using multiple projections, input arguments, or disparity functions to do so. we see that 4 projections or 4 representations leads to a better performance over using merely 1. Now that we've conducted an evaluation of stochastic grade, this leads us into a discussion. We note that functional correctness is only one aspect of grading, and there are other aspects like style or efficiency that also are important to grading that stochastic grade cannot yet handle. There's also grading inefficiency with correct programs, as we need to sample the maximum number of samples every time in order to make a decision about correct programs. Moreover, clustering uses disparity measures calculated from fixed sample sizes rather than the disparity metrics calculated directly from stochastic grade, which adds an extra step. And lastly, false rejection rate control requires a large solution sample size to have the theoretical guarantee, although this is not too much of a worry as sampling the large solution size takes only a few minutes at most. But more details about the system, some guidelines for practitioners, and how to best apply and use stochastic grade in a variety of problem contexts can be found in our paper, which is linked at the end of this presentation in a QR code. But for now, thank you so much for listening to this presentation.